Welcome to Talk Tensors. Today we are embarking on a deep dive into a stack of research that really, it forces us to completely re-examine the physical architecture of artificial intelligence.
Yeah, it really does.
We were looking specifically at a pretty seminal paper in computer science and machine learning. It's called DeepLab, Semantic Image Segmentation with Deep Convolutional Nets, Atrous Convolution, and Fully Connected CRFs.
A very long title, but an incredibly important piece of work.
Right, because for anyone working in dense prediction, this paper is absolutely foundational. We were going way beyond the standard classification problem here.
Exactly.
Like, it is one thing for a network to output a probabilistic label that, say, a dog exists somewhere in a photo.
Right, just a bounding box or a general label.
Yeah, but it is a completely different mathematical challenge to train a network to trace a microscopic pixel-perfect boundary around that dog.
To separate every single hair on its tail from the background carpet.
Exactly. That is the mission today. To figure out how they taught a machine to do that. And that gap in complexity is just staggering.
It really is. And to set the stage for you, when this paper was published, this was around 2015, 2016, the computer vision landscape was essentially bifurcated.
Right. There was a big divide.
Yeah. On one hand, you had these deep convolutional neural networks, or DCNNs, architectures like AlexNet and VGG16.
The heavy hitters of that era.
The absolute heavy hitters. They were dominating the ImageNet large-scale visual recognition challenge. Achieving unprecedented accuracy in object classification.
But, and this is the big but, those exact same architectures were proving remarkably clumsy when researchers attempted to repurpose them for semantic segmentation.
Very clumsy.
And I briefly want to highlight the authors on this paper before we get into why it was so clumsy. Liang Xi-shen, George Dependrio, Aisonus Cokinos, Kevin Murphy, and Alan L.U.
An absolute powerhouse team.
Right. And Alan L.U. actually previously worked on theoretical physics with Stephen Hawking before shifting over to AI at MIT and Harvard.
Which is just a crazy pedigree to bring to computer vision.
It really is. So we've got an amazing team and an amazing roadmap for this deep dive. We are going to start by understanding the invariance paradox. Then we'll explore the three massive contributions of DeepLab, which are atrous convolution, ASPP, and those fully connected CRFs.
Then we'll dive into the raw results they achieved.
Yep, and we'll cap it off with a novel notion segment looking at the future.
Sounds perfect.
Okay, let's unpack this. The fundamental flaw of those standard DCNNs when applied to semantic segmentation. It comes down to something the authors call the invariance paradox.
The invariance paradox.
Which makes perfect sense when you look at the fundamental design of something like VGG16.
Yeah.
The architecture was explicitly engineered to be spatially blind.
It had to be. To build a network that reliably classifies an object regardless of its position or scale or orientation, you have to intentionally destroy spatial variance.
Right. If a cat is in the top left corner or the bottom right corner, upside down or right side up, the network needs to just say cat.
Exactly. The network needs to aggregate local features into global concepts. It needs that built-in invariance.
But there is a massive cost to that invariance when you actually want to draw a border around the cat.
A huge cost. If we look at the tensor operations underlying that aggregation, we see exactly where the spatial destruction occurs.
It's the pooling, right?
Yep. It's driven by the repeated application of max pooling layers and convolutions with strides greater than 1.
Striding.
Right. So in a standard classification network, as the input image passes through successive layers, the spatial dimensions of the feature maps are aggressively downsampled.
Aggressively is the word.
It really is. A block of pixels is evaluated, the most prominent activation is passed forward through the max pooling operation, and the rest of the spatial data is just discarded.
It's thrown away.
Thrown away. The network trades spatial resolution for abstract semantic representation.
It stops processing a grid of RGB values.
And it starts processing abstract feature vectors, things representing textures, edges, and eventually object parts.
Let's quantify that destruction for a second, because the numbers in the paper really illustrate the severity of this bottleneck.
Let's do it.
In the original VGG16 architecture, this cascading sequence of pooling and striding reduces the spatial resolution of the final feature maps by a factor of 32.
A factor of 32.
32. So if we trace a standard 512 by 512 pixel input image through the network.
Pass pool 1, pool 2, pool 3.
Exactly. All the way to the final convolutional layers. That image has been compressed into a 16 by 16 feature map.
which is incredibly coarse.
Just a tiny grid.
Right. If you are attempting semantic segmentation, which requires assigning a class label to every single pixel in the original 512 by 512 image, working backward from a 16 by 16 abstraction is a geometric nightmare.
You literally don't have the data anymore.
No. The abstract semantic data is incredibly rich at that depth. The network is highly confident that a bicycle is present.
But the exact coordinates of the bicycle's tires.
Or the handlebars, they have been mathematically obliterated.
Mathematically obliterated. I love that. I often visualize this using a cartography analogy.
Oh, the map analogy.
Yeah. So imagine you are trying to draw a highly detailed, topologically perfect map of an entire city.
Okay.
Every sidewalk, every property line, every tree canopy perfectly outlined.
Sounds tough.
But the only reference material you are allowed to use is a photograph of the city that has been shrunk down to the size of a postage stamp.
Right. You're just squinting at this tiny thing.
Exactly. If you squint at the stamp, you can confidently say, oh, there is a park in the lower left and a cluster of skyscrapers in the center.
The semantic data is intact.
The semantic data is there. But if you try to draw a sharp, reliable boundary around a specific building on your full-size map, you simply cannot do it.
The local coordinate precision does not exist in reference material anymore.
Exactly. It's gone.
And this creates a cascade of specific challenges for dense prediction tasks. The researchers explicitly identify 3 hurdles they had to overcome.
Right.
First, the severely reduced feature resolution we just discussed. Second, the existence of multi-scale objects.
Which is tricky.
Very. A pedestrian could occupy 80% of the frame, or they could just be a cluster of 20 pixels in the background. And the network must segment both simultaneously.
Simultaneously, wow.
And third, the resulting poor localization accuracy, where the network outputs a generalized blobby mask rather than a sharp object boundary.
Like coloring with a thick marker.
Exactly. So this naturally sets up DeepLab's 3-part solution.
Okay, so let's get into solution number 1. How the DeepLab architecture addresses that first hurdle, the catastrophic loss of spatial resolution.
Because the brute force method of the era was terrible.
It really was. Back then, they used convolutional networks or transposed convolutions.
Right.
Researchers would let the network shrink the feature maps down to 16 by 16 and then attempt to artificially upscale those feature maps back to the original resolution using learned filters.
The deconvolutional approach, it works in theory.
In theory, sure.
But in practice, it is extraordinarily expensive in terms of computational overhead and memory allocation.
It's a memory hog.
A massive memory hog. It requires adding massive new layers to the network, which drastically increases the parameter count and slows down inference time.
Nobody wants a slow network.
No one.
Yeah.
Furthermore, upscaling a highly compressed feature map often results in checkerboard artifacts.
Oh yeah, those weird grid patterns.
Right, and smoothed over boundaries because you are trying to hallucinate spatial data that was permanently discarded during the max pooling phases.
You're asking the network to guess what used to be there.
Exactly.
Yeah.
So the DeepLab authors bypass the deconvolutional nightmare entirely.
And this is the part I love. They bypass it by borrowing a mathematical technique from the realm of multi-rate signal processing.
They integrate atrous convolution.
Yes, atrous convolution. The term atrous actually comes from the French phrase algorithme atrous, meaning algorithm with holes.
Algorithm with holes.
It's such a fascinating origin because this wasn't even a novel invention for deep learning, was it?
No, not at all. It was a revival of a technique developed in the 80s and 90s for computing the undecimated wavelet transform.
Which is just classic, taking old math and applying it to new problems.
What's fascinating here is how beautifully this decades-old signal processing technique maps onto the tensor operations of a modern neural network.
It's a perfect fit.
It really is. The fundamental goal is to compute feature responses at a higher spatial resolution without increasing the number of parameters or the computational complexity of the filter.
Without blowing up the memory budget.
Exactly. And standard convolution, a dense filter, say a 3x3 kernel slides across a feature map, computing the inner product at every position.
Right.
To increase the receptive field, which is the area of the original image that the filter actually sees, you historically had 2 choices.
And they were both bad.
Pretty much. Choice 1, increase the physical size of the filter, which squares the number of parameters. Choice 2, downsample the image, which destroys the resolution.
So atrous convolution introduces a third option.
The magic option.
The magic option. You explicitly control the density of the filter itself. You introduce a parameter called the rate, denoted as R.
The sampling rate.
Right. This rate dictates the stride with which we sample the input feature map. Mathematically, it is equivalent to injecting zeros, specifically r-1 zeros, between consecutive values of the filter.
Let's trace the exact 1D formula for this because the arithmetic is just so elegant.
Please do.
So for a 1D signal x of I and a filter w of k of length k, the atrous convolution output y of I is defined as the sum over k of x of I plus r times k, multiplied by w of k. When the rate r equals 1, this simply collapses into standard convolution.
There are 0 holes.
Exactly. But when r is greater than 1, you are essentially skipping pixels in the input signal. You are computing the inner product using spatially separated data points.
So if we translate that to a 2D feature map, it completely changes the effective size of the filter.
It expands it massively.
The paper provides a clean formula for this expansion. A standard filter of size, k by k, when injected with holes at rate r, operates with an effective size of k plus k minus 1 times r minus 1.
Exactly.
So let's say you have a standard computationally cheap 3x3 filter.
Okay.
If you set the atrous rate r to 2, you inject 1 0 between every filter weight. The effective size of your filter is now 5 by 5.
Right.
But if you set the rate to 12, you inject 11 zeros between every weight.
11 zeros.
Yeah. Your tiny 3x3 filter now possesses an effective receptive field of 25 by 25.
It covers a massive area of the feature map. It assimilates a vast amount of spatial context, but, and this is the crucial part, it still only requires 9 multiplication operations per position.
The parameter count remains identical to the standard 3x3 filter. That is incredible.
It's free real estate.
It is. I visualize this as replacing a solid wall with a chain link fence.
Oh, that's a good way to look at it.
Yeah, so if you were standing behind a solid brick wall and looking through a single peephole, your field of view is incredibly narrow.
Very restricted. That is your standard dense filter.
Exactly. If you want to see the entire yard, the traditional DCNN approach was to physically step back.
Effectively shrinking the yard into a smaller abstract representation.
Right. But the atrous approach says, instead of stepping back and losing the crisp details of the grass, let's just replace the brick wall with a chain link fence.
The physical amount of material, the metal links, is the exact same as the brick wall.
The computational weight hasn't changed.
Right.
But the holes in the fence allow you to see a dramatically wider field of view without ever having to shrink the environment.
It is a brilliant workaround for the invariance paradox.
It completely sidesteps it.
By replacing standard convolutions with atrous convolutions in the deeper layers of the network.
Specifically modifying the stride of the pooling layers, right?
Yes, modifying the stride and applying the atrous rate to the subsequent convolutions. The DeepLab system intercepts the downsampling problem before it becomes catastrophic.
So instead of letting the resolution drop by a factor of 32,
they control the decimation, they keep the spatial resolution at a factor of 8.
That is a massive difference from a tiny 16 by 16 grid to a much more manageable resolution.
It saves a massive amount of spatial detail.
But wait, I have a question about this. If we are injecting zeros into the filter, doesn't that inherently mean we are skipping over data?
That's a very common concern.
Like, if my filter is looking at pixel 1 and pixel 13 and ignoring everything in between, aren't we risking missing thin, delicate structures entirely?
Like an aliasing effect.
Yeah. If a single wire or a blade of grass falls perfectly into one of those holes, the filter mathematically cannot see it. How does the architecture avoid that aliasing issue?
That is a crucial question regarding the physics of the sampling.
It seems like a glaring flaw if you just look at the math.
Right, and if you were applying an atrous filter with a massive rate directly to the raw, high-frequency RGB image, you absolutely would experience severe aliasing. You would miss those thin structures.
Okay, so why doesn't it happen here?
Because in the DeepLab architecture, these high-rate atrous convolutions are applied deeply within the network.
Wow.
Typically at block 4 or block 5 of the ResNet architecture.
So the data has already been pre-processed.
Precisely. By the time the feature map reaches these deep atrous layers, it has already passed through numerous standard convolutions and a few pooling operations.
Not raw pixels anymore.
Exactly. The feature map is already somewhat dense and aggregated. A single pixel in a deep feature map already represents a receptive field of local pixels from the original image.
Oh, I see. So the whole isn't actually skipping raw pixels, it's skipping between aggregated conceptual blocks.
Yes. Furthermore, the atrous filters are applied in a sliding window fashion, evaluating every position across the feature map.
So they overlap anyway.
The overlapping nature of the computation ensures that local features are captured, while the wide span of the atrous weights assimilates the broader context.
Okay, that makes perfect sense. And the empirical results of this optimization are just staggering.
They really are.
They took the FC6 layer of the VGG16 network and ran an ablation study. When they used the standard dense formulation, it had a specific baseline performance, but was highly inefficient.
Very bloated.
But by switching to a 3x3 kernel with an aperture sampling rate of 12, they maintained the exact same receptive field and performance.
But the computation was 3.36 times faster.
3.5 times faster. And they slashed the number of parameters from a bloated 134.3 million down to just 20.5 million.
That fundamentally changes the memory economics of the network.
It takes it from impossible to highly practical.
Exactly. Atrous convolution gives the architect a precise dial. You can tune the rate parameter to find the optimal balance between tight, localized feature extraction and broad global context assimilation.
But as we transition to the second major challenge, multiscale object segmentation, we see that relying on a single setting on that dial is often insufficient for complex scenes.
Here's where it gets really interesting.
Yes, because this is where we encounter the limitations of a fixed receptive field.
Right.
Like if we are analyzing a photograph of a busy urban intersection, the scale variance is extreme.
You have objects of completely different sizes everywhere.
Exactly. A pedestrian standing directly in front of the camera might occupy a massive region of the tensor. Their face alone might be 200 by 200 pixels.
But conversely, a pedestrian standing 3 blocks down the street might only occupy a 10 by 20 pixel cluster.
And the neural network has to identify both of them as a person.
Simultaneously.
A neural network equipped with a fixed receptive field will inevitably struggle with this.
It has to pick a lane.
Right. If the filter is small, it flawlessly segments the distant pedestrian, but gets lost in the texture of the nearby pedestrian's coat.
It fails to recognize the coat as part of a human.
Yeah. But if the filter is massive, it captures the nearby pedestrian perfectly, but completely smooths over the distant pedestrian.
Treating them as background noise.
Exactly. So this multi-scale existence is a notorious problem in computer vision.
It is. And the traditional method for addressing this was to utilize image pyramids.
Image pyramids. Just the name sounds exhaustive.
It was. You would take the original raw image and generate multiple scaled versions. A high-resolution version, a medium-resolution version, and a heavily downsampled version.
Okay.
You would then feed all of these distinct images into parallel instances of the deep convolutional neural network, extract the feature maps from each scale, resize them back to a common resolution, and fuse them together.
That sounds computationally punishing.
It is.
You're asking the GPU to run the entire VGG16 or ResNet backbone multiple times for every single frame of inference.
It was incredibly resource-intensive.
I can't even imagine the latency on that.
While feature extraction through image pyramids yields excellent results because it explicitly captures multi-scale context, it is painfully slow and memory-bound.
It's just not practical for real-time applications.
No. So the DeepLab authors sought a mechanism to achieve the benefits of the image pyramid without the computational nightmare of running the deep network multiple times.
And this leads to their second major architectural contribution.
Yes. They drew inspiration from earlier spatial pyramid pooling methods, but they supercharged the concept using their newly integrated tool.
Aisonus convolution.
Exactly. This led to atrous spatial pyramid pooling, or ASPP.
ASPP. The mechanics of ASPP are incredibly elegant.
They really are. Instead of resampling the incoming image at different scales, ASPP probes the deep convolutional feature layer with multiple parallel filters.
But each filter's fundamentally different, right?
Yes, each utilizing a fundamentally different atrous sampling rate. The paper details an architecture they refer to as DeepLab ASPPL, which deploys 4 parallel branches operating on the exact same incoming feature map.
Let's examine the tensor dimensions of those branches, because it paints a great picture.
Sure.
The network splits the feature map into 4 parallel pathways. The first branch might probe the data with a 3x3 atrous filter utilizing a rate of 6.
The second branch uses a rate of 12.
The third branch uses a rate of 18.
And the fourth branch uses a massive rate of 24.
And because of the expansion formula we discussed earlier, that fourth branch with a 3x3 filter and an atrous rate of 24 behaves as if it has an effective filter size of 49 by 49.
Exactly. All 4 of these parallel branches are probing the identical feature layer simultaneously.
At the exact same time.
Yes. But each branch is capturing a completely different magnitude of spatial context.
So the branch with a rate of 6 has a relatively tight field of view.
It is highly sensitive to fine localized details, the curvature of a side mirror or the shape of a traffic light lens.
But the branch with a rate of 24 possesses a massive field of view.
It is capturing the global scene geometry. It assimilates the fact that the side mirror is attached to a vehicle, which is situated on a paved road surrounded by buildings.
I think of ASPP like a highly advanced multi-lens camera rig.
A multi-lens camera, I like that.
Yeah, so imagine standing at an observation deck looking out over a valley. Instead of looking through a single lens, you are looking through 4 distinct lenses simultaneously.
Okay, I'm picturing it.
Lens 1 is a macro lens, capturing the intricate veins on a leaf directly in front of the glass. Lens 2 is a standard 50mm lens capturing the tree.
Lens 3 is a wide-angle lens capturing the forest canopy.
Exactly. And lens 4 is a telephoto lens capturing an eagle flying miles away.
And your brain processes all 4 optical feeds simultaneously,
seamlessly fusing the microscopic details with the vast macroeconomic context of the environment. ASPP provides that exact multi-lens capability to the neural network.
And the tensor fusion at the end of the ASPP block is quite straightforward.
How do they stitch it all back together?
Once each of the 4 parallel branches computes its atrous convolutions, the resulting feature maps are concatenated along the channel dimension.
Just stacked together.
Exactly. This massive context-rich tensor is then passed through a 1-by-1 convolution.
Ah, a bottleneck layer.
Right, which acts as a dimensionality reduction bottleneck, blending the multi-scale features together and projecting them down to the final number of target classes.
That is so clean. And the performance leap achieved by ASPP is highly quantifiable.
The numbers don't lie.
No, they don't. When they tested this on the Pascal VOC 2012 dataset, adding the multi-branch ASPP system provided a massive boost over using a single field of view.
Massive.
They reached a mean intersection over union, which, for you listening, is a metric that calculates the overlap between the predicted segmentation mask and the actual ground truth mask.
How well the prediction matches the reality.
Exactly. They reached a mean IOU of nearly 71.6% solely from this architectural enhancement.
Just from adding ASPP.
Just from that.
Yeah.
The network was now robust to scale variations and was computing at a fraction of the cost of traditional image pyramids.
It's a huge win. Yet, even with a atrous convolution preserving the spatial resolution at a factor of 8,
Right.
and ASPP flawlessly handling the multi-scale object detection.
They still weren't done.
No. The DeepLab system was still battling the 3rd and final hurdle of the invariance paradox.
For the localization accuracy at the extreme edges of objects, the boundary problem.
The boundary problem.
Because up to this point in the pipeline, the deep convolutional neural network, even armed with injected holes and spatial pyramids, is still essentially coloring with a thick, blunt highlighter.
A blunt highlighter, that's exactly what it looks like.
The network is phenomenally intelligent at identifying that a specific cluster of pixels represents a human, but the edges of its prediction bleed over the actual lines of the human's body.
The output mask is a blobby, undefined silhouette.
It looks like a cloud shaped roughly like a person, not a crisp, anatomically perfect segmentation.
Right. Which raises a fundamental architectural question. How do you force the neural network's high-level semantic knowledge to respect the low-level physical boundaries present in the raw input image?
How do you teach it to color inside the lines?
Exactly. And to solve this, the researchers made a fascinating pivot.
They went totally outside the deep learning box.
They temporarily turned away from the deep learning paradigms of the 2010s and looked back at probabilistic graphical models.
Which is such a cool move.
Specifically, they introduced a fully connected conditional random field, or CRF.
Now, integrating CRFs into deep learning pipelines wasn't entirely unprecedented.
No, it had been done.
But the historical application was significantly limited compared to what DeepLab implemented.
Vastly different. Historically, researchers utilized short-range CRFs.
Short range.
Right. A short-range CRF operates on a localized neighborhood graph. It only looks at the immediate adjacent pixels to smooth out local noise.
It acts essentially as a localized smoothing filter, cleaning up minor artifacts in the DCNNs prediction.
However, the DeepLab authors recognize that short-range CRFs fail catastrophically when presented with thin, intricate structures or long-range dependencies.
Because it just smooths them away.
Exactly. If you have the thin leg of a wooden dining chair, a short-range CRF will likely smooth it entirely out of existence because, compared to the larger mass of the chair seat, the thin leg appears as anomalous local noise.
The system thinks, oh, that's just a weird error. Let me blur that out.
Right. To overcome this, DeepLab utilizes a fully connected CRF.
And fully connected is not an exaggeration here.
No, it is literal.
It mathematically connects every single pixel in the image to every other pixel in the image.
Every single one.
If you're processing an image with 1 million pixels, the CRF is evaluating the probabilistic relationship between pixel number 1 and pixel number 999,999.
Regardless of how far apart they are on the spatial grid.
The scale of that computation seems impossibly dense.
It is a massive computational graph. And to understand why it works so brilliantly, we have to look closely at the energy function it seeks to minimize.
Let's do some math.
Okay, the fully connected CRF models the segmentation task as an energy minimization problem.
The energy function, denoted as E of X.
Yes. It assigns a penalty score to any given segmentation configuration. The goal of the inference algorithm is to find the label assignment X that results in the absolute lowest possible energy score.
We want the lowest penalty.
Exactly. And this function, E of X, is constructed from two distinct components.
The unary potential and the pairwise potential.
Let's define the unary potential first.
The paper denotes this as theta sub I of X sub I.
This is essentially the deep neural network's initial guess. It is computed directly from the logits output by the DCNN.
So it's basically the probability map.
Yes. Mathematically, it is the negative log likelihood of the label assignment. So if the DCNN is 99% confident that a specific pixel belongs to the motorcycle class, the unary potential assigns a very low energy penalty to that label.
Because it matches the guess.
Right. But if the network thinks there is only a 1% chance it's a motorcycle, the unary potential assigns a massive energy penalty.
It is just taking the probability distribution from the ASPP output and translating it into an energy cost.
Precisely. The unary potential relies entirely on the abstract semantic intelligence of the deep network.
It trusts the deep learning.
It does. But the true magic of the boundary refinement happens in the pairwise potential.
Denoted as theta sub I of X sub I, X sub J.
Yes. The pairwise potential operates independently of the deep network's semantic understanding.
It doesn't care what the DCNN thinks.
Not at all. It looks strictly at the raw original RGB image. It acts as a rigorous, low-level referee that dictates how adjacent and distant pixels should relate to one another.
And it does this by establishing a penalty system based on visual similarity.
Yes.
The pairwise potential heavily penalizes the system if it assigns different class labels to pixels that look visually identical.
Exactly. The mathematical formulation of the pairwise potential in DeepLab is based on a label compatibility function multiplied by a linear combination of Gaussian kernels.
Okay, that's a mouthful. Let's break that down.
Sure. The label compatibility function, often modeled as a simple Potts model, is a binary switch.
On or off?
Exactly. It only applies the penalty if the proposed labels for pixel I and pixel J are different. If the labels are the same, the penalty is 0.
So if the system tries to say pixel A is a dog and pixel B is a cat, the Potts model activates the penalty.
Right.
But how does it decide how big that penalty should be?
That is dictated by the bilateral Gaussian kernels.
Ah, the kernels.
Which compute the affinity between the two pixels based on two specific observations, their physical distance from each other and their color difference in the RGB space.
So position and color.
DeepLab utilizes two distinct kernels. The first is an appearance kernel.
This kernel looks at the spatial position of the pixels P sub I and P sub J and the color intensities of the pixels I sub I and I sub J.
Right. And it is controlled by two hyperparameters.
Theta sub alpha.
Which dictates the scale of the spatial distance.
And theta sub beta.
Which dictates the scale of the color contrast.
Let's pause on those parameters for a second because they really control the behavior of the edge snapping.
They are the tuning knobs.
Right. If theta sub beta is set very low, it means the kernel is highly sensitive to color shifts.
Highly sensitive.
So if two pixels are even slightly different shades of blue, the kernel says, these are different, don't force them to share a label.
But if they are the exact same hex code of blue, and they are spatially close, according to theta sub alpha, the appearance kernel outputs a massive penalty if the network tries to assign them different classes.
That is the core mechanism of the boundary recovery. That's the secret sauce.
It really is. Let's say you have a cluster of pixels that are all the exact same shade of metallic chrome, representing the exhaust pipe of a motorcycle.
Okay, metallic chrome.
The appearance kernel forcefully binds them together. If the DCNN's unary potential tries to lazily label half of that chrome pipe as background road.
Because it's a blunt highlighter.
Right. The pairwise penalty skyrockets because it recognizes that the chrome pixels are visually identical and tightly clustered.
So the energy function forces the semantic labels to align with the high contrast physical edges present in the raw photograph.
Exactly. It forces the mask to snap to the chrome pipe.
And there is a second kernel as well, the smoothness kernel.
Yes. The smoothness kernel operates solely on the spatial positions P sub I and P sub J, ignoring color entirely.
It doesn't care about RGB.
Not at all. It is controlled by the hyperparameter theta sub gamma. This kernel acts as a structural enforcer.
What does that mean in practice?
It penalizes small, isolated regions of differing labels. It effectively removes isolated false positives.
Oh, okay.
If the DCNN randomly guesses that a single pixel in the middle of a vast, featureless blue sky belongs to the dog class.
Which happens.
It does. The smoothness kernel recognizes that this pixel is spatially surrounded by sky pixels, and it applies a penalty to smooth out that erroneous local anomaly.
It basically says, there's no way there's a one-pixel dog in the middle of the sky. Let's fix that.
Precisely.
Okay, but we have to acknowledge the computational elephant in the room here.
Let's talk about the elephant.
If this energy function is evaluating every single pixel against every other pixel using complex Gaussian kernels, how does it compute in any reasonable time frame?
It's a massive matrix.
You mentioned it's a fully connected graph of millions of nodes. Standard message passing algorithms would take hours, if not days, to run inference on a single image.
You are absolutely correct, and this was the historical barrier to using fully connected CRFs. The exact computation of the partition function for this graph is mathematically intractable.
You just can't do it.
You can't. However, the DeepLab authors leveraged a highly efficient mean field approximation algorithm developed by Cranboul and Colton.
Cranboul and Colton.
Yes. This algorithm approximates the complex message passing steps by expressing them as convolutions in a high-dimensional space, specifically utilizing a permutohedral lattice.
A permutohedral lattice. That is some serious geometry.
It is a profound mathematical trick. It reduces the complexity of the inference from quadratic time to linear time.
From quadratic to linear, that's everything.
It allows this incredibly dense, fully connected probabilistic graph to be evaluated in a fraction of a second.
Which makes it actually useful for real application.
Exactly.
The visual evidence of this mathematical synergy is absolutely stunning.
The figures in the paper are just beautiful.
They really are. If you look at Figure 6 and Figure 12 in the DeepLab paper, the before and after evaluations of the CRF are striking.
Figure 6 is the airplane, right?
Yeah, in Figure 6, there is an image of a commercial airplane sitting on a tarmac.
Okay.
Before the fully connected CRF is applied, the DCNN's prediction is just a nebulous red blob.
You can recognize the general shape of an aircraft, but the landing gear is an indistinguishable smudge.
And the sharp angles of the tail fin bleed softly into the sky. It's very soft.
Then you look at the after CRF column.
Right in day.
The mean field inference has minimized the energy function, and the red semantic label has snapped perfectly to the intricate contours of the plane.
The wheels are perfectly isolated from the concrete.
Every geometric angle of the tail fin is razor sharp.
It's incredible. And the motorcycle example in that same figure provides an even better illustration of the appearance kernel in action.
Oh, the custom chopper.
Yeah, it is a photograph of a custom chopper with sweeping, complex handlebars and a highly intricate engine block.
Very difficult geometry for a network.
So difficult. Before the CRF, the DCNN outputs a generalized green cloud that covers the bike and portions of the rider.
It's just a green haze.
But after the CRF evaluates the pairwise potentials, comparing the RGB color vectors of the chrome, the black letter seat, and the background environment, the label mask shrinks and molds itself flawlessly to the chrome pipes.
The precise curve of the tires.
And the shape of the rider's legs, like shrink wrap.
Shrink wrap is a great analogy.
There's also Figure 12 from the Pascal person part dataset.
That dataset is notoriously difficult.
Because it requires the network to segment the human body into discrete parts. The head, the torso, the arms, and the legs are all distinct classes.
And the image shows a baby sitting on the floor.
Right. Before the CRF, the boundary between the baby's arm and his torso is totally blurred. The network knows it's all baby, but the specific parts overlap.
But after the CRF, the algorithm perfectly traces the line where the baby's sleeve ends and its exposed arm begins.
The CRF detects that subtle shift in pixel texture and color intensity across the sleeve boundary, and it forces the segmentation mask to respect that physical line.
It is literally teaching the machine to color inside the lines with absolute pixel-perfect precision.
It's just awe-inspiring when you really think about the math behind it.
The integration of the fully connected CRF transformed the DeepLab system from a robust semantic classifier into an unparalleled dense prediction engine.
It really did. By coupling the powerful recognition capacity of the DCNNs for the unary term with the fine-grained localization accuracy of the CRF for the pairwise term,
they achieved boundary recovery at a level of detail that was completely beyond the reach of any existing methodology at the time.
And with the three core pillars of the architecture established, atrous convolution, ASPP, and the fully connected CRF, the researchers then initiated what we might call the architecture wars.
The engine upgrade.
Exactly. They had built this incredible processing pipeline, but they realized they could further optimize the underlying engine driving the unary potentials.
Because the initial iterations of DeepLab were built utilizing the VGG16 backbone.
Which was great, but deep learning is a fast-moving field, and deeper, more sophisticated networks were emerging.
Yes, the DeepLab authors transitioned their system from the massive 134.3 million parameter VGG16 network to the newer, highly efficient ResNet 101 architecture.
ResNet, or residual networks, they fundamentally altered deep learning
by introducing the concept of identity mappings, or skip connections.
Since you listening are probably familiar with the vanishing gradient problem, we understand that traditional sequential networks degrade in performance as they get deeper.
The signal just dies out.
Right. ResNet solves this by allowing the input of a convolutional block to bypass the block and be added directly to the output.
The simple addition function, h of x equals f of x plus x, allows networks to scale to hundreds of layers without stalling.
But the DeepLab authors discovered that these skip connections offered a massive secondary benefit, specifically for semantic segmentation.
Because the raw data tensor X is constantly bypassing the convolutional bottlenecks and flowing deeper into the network, ResNet intrinsically preserves spatial coordinate data far better than VGG16's strict sequential processing.
It holds onto the math coordinates.
Exactly. To prove this, they conducted a highly specific analysis called a trimap evaluation.
What's fascinating here is how they visualize this. It's beautifully shown in Figure 10.
A trimap evaluation does not look at the overall accuracy of the segmentation mask. Instead, it measures accuracy exclusively along the extreme edges of an object.
You take the ground truth boundary of the object, and you draw a narrow band around it, perhaps just 2 pixels wide or 10 pixels wide.
A tiny ribbon.
You then calculate the network's prediction accuracy strictly within that tiny, narrow ribbon. It isolates how well the network handles the most difficult aspect of segmentation, the exact transition border.
And the trimap results were a revelation regarding the power of residual networks.
Use this revelation.
They found that the identity mapping in ResNet 101 was so intrinsically powerful at holding on to spatial features from intermediate layers that its raw boundary predictions, before applying any CRF post-processing, were almost as accurate as the older VGG16 network's predictions after the CRF was applied.
That is wild. The baseline spatial acuity of ResNet was simply superior out of the box.
It is a profound testament to how rapidly the underlying DCNN architectures were evolving.
However, the fully connected CRF was not rendered obsolete by this.
Not at all.
When they took that already excellent ResNet 101 output and passed it through the mean field inference of the CRF, the accuracy within those narrow trimap bands jumped even higher.
The CRF remains strictly critical for removing isolated false positives and achieving that absolute pixel-perfect snap based on low-level color contrasts.
It's still the ultimate referee. Let's run through the spectacular leaderboard results, because the performance metrics of the ResNet 101 DeepLab variant absolutely dominated the field.
The scores were incredible.
On the notoriously difficult Pascal VOC 2012 benchmark, their best model utilizing ResNet 101, atrous spatial pyramid pooling, multi-scale inputs, and the fully connected CRF reached an astonishing 79.7% mean intersection over union on the official test set.
At the time of publication, that was the absolute state of the art.
Nobody could touch it.
And they demonstrated remarkable versatility across distinct datasets. They achieved state-of-the-art results on Pascal context, which test the network's ability to segment background stuff like water, sky, and grass rather than just distinct foreground objects.
Stuff versus things.
Right. They also succeeded on the Pascal person part dataset we mentioned earlier, achieving 64.9% mean IOU by successfully distinguishing the microscopic boundaries between human body parts.
And they also pushed the architecture into the highly complex domain of autonomous driving, testing it on the Cityscapes dataset.
Cityscapes is a massive collection of high-resolution urban street scenes.
Very noisy data.
It requires the network to navigate extreme clutter, overlapping instances of pedestrians, and vast disparities in scale. A massive transport truck passing directly next to the camera while a traffic light exists 200 meters down the road.
DeepLab scored a 70.4% mean IOU on the Cityscapes validation set, proving that the synergy of ASPP and CRFs was robust enough to handle the chaotic visual environment of real-world navigation.
If we connect these accuracy metrics to the broader picture of real-world deployment, what truly matters is the computational speed.
Accuracy is nothing if it takes a week to process a frame.
Exactly. The authors explicitly emphasize this advantage. Because they utilized an atrous convolution to preserve resolution instead of relying on memory-hogging deconvolutional layers, their dense DCNN pipeline could process images at 8 frames per second on an NVIDIA Titan X GPU.
8 frames per second is nearing the threshold of real-time processing for video feeds.
Precisely. And the mean field inference required to evaluate that massive, fully connected probabilistic graph across millions of pixel pairs.
The CRF inference.
Through the Permito-Hedral lattice approximation, it took merely 0.5 seconds on a standard CPU.
Half a second. On a CPU.
The entire DeepLab system is composed of just a cascade of 2 highly optimized, well-understood mathematical modules, DCNNs and CRFs.
It demonstrated to the field that you do not need a convoluted, hypercomplex pipeline of 10 distinct brittle algorithms to achieve state-of-the-art dense prediction.
You simply require a spatially aware network and a strict, probabilistic referee.
But, as with any truly rigorous scientific paper, the authors exhibit profound intellectual honesty regarding the limitations of their architecture.
Which is always refreshing to see.
They do not just parade the flawless segmentations of airplanes and motorcycles. They explicitly dedicate a section of the paper, and Figure 14, to analyzing exactly where their brilliant system falls apart.
I appreciate this immensely. It provides a clear roadmap for the next generation of researchers.
Analyzing failure modes is essential for architectural evolution. If a paper claims a system is flawless, the evaluation is likely flawed.
The DeepLab authors direct the reader's attention directly to their failures, and these failures share a highly specific geometric characteristic, incredibly delicate, ultra-thin boundaries.
The 2 examples highlighted in Figure 14 are heartbreakingly difficult for a convolutional network.
Let's talk about the bicycle first.
Yeah, the first is a bicycle. A person is riding the bike, and the system needs to segment both the human and the machine.
The tubular frame of the bike is segmented adequately.
But the wire spokes of the bicycle wheels are practically invisible to the network.
The system simply hallucinates a solid, ugly blob over the entire wheel. It completely fails to segment the empty background space between the microscopic metal spokes.
It just gives up. And the second example is a slender wooden dining chair sitting on a patterned carpet.
The system successfully captures the solid seat and the backrest.
But the thin, vertical wooden legs of the chair vanish entirely into the background noise. It's like the chair is floating.
This specific failure mode raises a vital question regarding the architecture. Why does the mighty fully connected CRF, which we just lauded for snapping perfectly to the thin arms of a baby or the chrome pipes of a motorcycle, fail so completely on a chair leg?
That is the big question.
The answer lies directly in the mathematics of the energy function we unpacked earlier. Recall that the unary term, the DCNN's logic prediction, is the absolute foundation of the energy state.
The initial guess.
Yes. The CRF is a post-processing refinement tool. It does not generate semantic knowledge. It requires a baseline level of confidence from the neural network to know where to begin refining.
The CRF is essentially the world's greatest copy editor.
That's a great way to think of it.
The copy editor can fix your grammatical errors, sharpen your vocabulary, and align your formatting perfectly.
But if you hand the copy editor a completely blank sheet of paper, they cannot manifest an essay for you.
Exactly. For the bicycle spokes and the chair legs, the initial DCNN is completely unconfident.
Despite the atrous convolutions preserving resolution at a factor of 8, the feature maps have still been downsampled just enough that those microscopic single pixel-wide details are permanently destroyed before the network ever reaches the classification layer.
If the unary potential outputs a near 0% probability that a chair leg exists in a specific spatial region, the pairwise potential of the CRF has absolutely nothing to grab onto.
You cannot snap a boundary to an object if the deep network does not even acknowledge the object's existence.
It's blind to it.
The authors acknowledge this limitation openly, recognizing that downsampling by a factor of 8 is still a lossy compression.
And brilliantly, they actually foreshadow the architectural paradigm shift that the field would eventually adopt to solve this.
In their conclusion, they speculate that integrating an encoder-decoder structure, specifically referencing concurrent works that exploited high-resolution feature maps retrieved via a decoder path, might be necessary to recover these ultra-delicate details.
They essentially pointed a mathematical signpost toward architectures like UNet,
which would subsequently dominate fields like medical image segmentation, where the microscopic boundary of a cellular structure or tumor is literally a matter of life and death.
They understood the absolute limits of their atrous approach, and they accurately predicted the mechanisms the next era of machine vision would require.
It is the mark of incredible scientific rigor to build the most accurate system in the world and simultaneously draft the architectural blueprint for how to eventually defeat it.
Well said. We have covered a massive amount of technical ground today. Let's do a quick synthesized recap of the elegant synergy of the DeepLab architecture before we launch into our final segment.
A quick summary, let's do it.
First, they leveraged deep convolutional neural networks, specifically utilizing the identity mappings of ResNet 101 for their raw, unbeatable semantic power, their ability to extract abstract feature representations.
Second, they deployed atrous convolution, the algorithm with holes, to explicitly control the field of view, expanding the receptive field to assimilate vast spatial context without destroying the spatial resolution or exploding the parameter count.
Third, they introduced atrous spatial pyramid pooling to act as a multi-lens temporal array, probing the deep feature maps with parallel filters at distinct rates to capture objects at wildly different scales simultaneously.
And finally, they integrated a fully connected conditional random field, utilizing mean field inference to act as the ultimate probabilistic referee, forcing the network's semantic logics to perfectly align with the low-level RGB color contrasts and spatial geometry of the raw image.
It remains a masterclass in cross-disciplinary synthesis.
It really is. The architecture beautifully weaves together undecimated wavelet, transforms from signal processing, deep residual learning from computer vision, and probabilistic graphical models from classical machine learning into a single, cohesive, world-beating pipeline.
The legacy of DeepLab is evident in almost every dense prediction task deployed today. The concept of utilizing dilated or atrous convolutions to maintain spatial fidelity without parameter bloat is now a standard, indispensable tool in the deep learning utility belt.
It's ubiquitous.
Which brings us to my favorite part of the deep dive. It is time for our novel notions segment.
I've been waiting for this.
I must issue our standard ironclad disclaimer right up front. The ideas discussed in this segment are for entertainment, imaginative, and theoretical extrapolation purposes only.
We are just having fun with the math here.
We are engaging in a thought experiment, stretching the tensor math from the DeepLab paper into outlandish but logically plausible new territories. Do not attempt to secure venture capital funding based on this discussion without doing your own rigorous peer-reviewed mathematics.
Definitely not. So what's the pitch?
Here is the pitch. DeepLab proved that atrous convolution inserting explicitly controlled holes into our observation filters is an incredibly efficient way to gain massive contextual awareness without drowning in data or losing resolution.
Agreed.
But they applied this strictly to 2D spatial matrices, the X and Y coordinates of a photograph.
Right.
What if we take the exact same mathematical principle, the exact same expansion formula, but instead of applying it to spatial images, we apply it to time?
Time.
What if we construct an atrous temporal pyramid?
Okay, that is a highly compelling translation of the tensor mechanics.
Right.
If we examine complex 1D time series data, researchers frequently encounter the exact same invariance paradox that DeepLab faced with 2D images.
The exact same one.
Consider high-frequency algorithmic trading data, or the global telemetry from meteorological weather patterns.
Let's use the stock market as the example.
Sure. If you are attempting to analyze the stock market, you could technically ingest the order book at every single microsecond.
But the sheer volume of that data sequence is so overwhelmingly massive that any recurrent or temporal convolutional network would experience parameter explosion, and the inference time would be completely unmanageable.
It would crash. So what is the standard practice for data scientists?
They downsample.
They do. They take the microsecond trading data, apply a max pooling operation, and compress it into daily moving averages or weekly candlestick charts.
But mathematically, just like shrinking the detailed neighborhood map down to a postage stamp, when you downsample time into daily averages, you permanently destroy the high-resolution temporal reality.
You lose the crucial momentary spikes.
You entirely miss the microscopic millisecond flash crash that triggered a massive multi-day institutional sell-off.
You lose the exact temporal boundary of the event.
Therefore, an atrous temporal pyramid could resolve this by scanning the 1D time series data using parallel filters with expanding temporal gaps.
Let's visualize that tensor structure. Instead of a 3x3 spatial filter, imagine a 1D temporal convolution kernel of size 3, looking at 3 specific data points in time.
Okay, kernel of size 3.
Your first parallel branch, with an atrous rate of 1, looks at 3 consecutive microseconds. It acts as the macro lens, analyzing high-frequency volatility.
Your second branch, with a rate of 1,000, looks at a microsecond, skips 1,000 microseconds, looks at another, and skips 1,000 more.
And your fourth branch, utilizing a massive rate of 1 million, is effectively sampling data points spaced days or weeks apart.
And you execute all of those temporal branches in parallel, identically to ASPP.
Simultaneously, the network is processing the exact same incoming sequential data stream, but it is assimilating temporal context across completely distinct scales of time.
It could simultaneously capture the microscopic anatomy of an algorithmic flash crash in branch 1, while branch 4 is recognizing that this specific flash crash perfectly aligns with a multi-year macroeconomic cycle.
And it computes all of this in a single forward pass, without needing to artificially compress or stretch the timeline, and without requiring a recurrent network to hold 1 million steps of memory.
The tensor architecture is entirely mathematically sound.
You could even extend the analogy and append a temporal CRF at the end of the pipeline.
A temporal CRF.
A pairwise temporal potential that evaluates the raw sequence data and states, wait, the volatility index at timestamp t is mathematically identical to the volatility index at timestamp t minus 2 seconds. These distinct moments must belong to the exact same market state classification,
forcing the temporal model to snap its phase predictions to the exact millisecond the market environment shifted.
The mathematical translation from 2D space to 1D time is practically seamless. It is a brilliant architectural notion.
The versatility of foundational mathematics is continually astounding. As we conclude this deep dive, I want you, the listener, to perform a brief cognitive experiment.
A little homework.
Look around the room you are currently occupying. Focus your vision on a specific object. A chair, a potted plant, or a coffee mug.
Notice how instantly and effortlessly your own biological neural network, your visual cortex, segments the thin, delicate legs of the chair from the texture of the carpet it rests on.
You do not consciously compute the color contrast. You simply perceive the physical boundary perfectly and intuitively.
It happens in milliseconds.
Take a moment to truly appreciate the absolute, mind-bending matrix arithmetic, the probabilistic graphical modeling, the raw computational engineering it required for researchers to teach a machine made of silicon and code to replicate that exact biological function.
To teach a network not simply to output a probability that a chair exists, but to deeply understand and trace its physical spatial reality within the universe.
It is a stunning triumph of computer science. Thank you for joining us on Talk Tensors. Keep questioning the boundaries of the architecture, and we will catch you on the next deep dive.